Okay, welcome back to chapter 22 again on negative feedback. This is part 4. And in this part, we're going to look at stability. Okay, stability. So what we'll do is we'll look at a 2-step, 3-step, and then 4-step pathway. So we'll start off with the simplest. And this is stability with negative feedback, of course. And for the simplest one, it's just going to be that. Okay. Let's write down this is the simplest one to deal with. So n is 1 minus 1. I suppose I should put these down here. So n equals 1, r equals 2. The input doesn't matter. We'll just have 1 here because what we're really after is the characteristic equation. Okay. So I don't care about the input in that case. So we'll compute this. Remember this, it's Si minus n dv dx. Now, just to add, when you're computing the characteristic equation has to include the full thing, including the s. Okay, it has to be at all frequencies. You can't set s to 0 and then do it. You have to do it with s there present. Okay, so what we need to do is to determine this. We don't care about that. So I is basically going to be 1. So let's do that. So it's s minus. Now this thing n, I guess I should let me write down dv by dx is the critical vector or matrix, depending on how size of the system. dv1 dx, dv2 dx. Oops. Okay. And so that's 1 times that minus 1 times that. So we end up with dv1 dx minus dv2 dx. Okay. And of course, I want the inverse of that. All right. So that's pretty easy to do. So that's s minus, and I'll just swap these terms around. Actually, put a plus this and then swap these terms around. v2 over dx minus dv1 dx. If you want to do the full inverse, it's just that. Now, this is the characteristic equation. Okay. So all I have to do is set that up. Okay, equals 0, and I'm looking for the roots s. Okay, so what can we say about these terms? Well, first of all, this one here, this one is oops, sorry. This one is dv2 dx. So that's that one. This one is positive, okay, because x enhances the reaction rate. So this is positive, okay? So I'll put a positive here. All right. This one here is dv1 dx. That's negative because that's inhibition, so it's negative. So this is negative. But of course, we have a negative here, so this whole thing is positive. So therefore, this whole thing is positive. So the root, there's only a single root. S must be less than 0, okay, in order for that to be satisfied. And since it's less than 0, it is stable. Always. So long as these two conditions are satisfied, this thing is always stable, all right, no matter what. So that was the easy one. So now let's on to do the next one. Let me see, let's try this, shall we? So x1, x2, okay, and then the negative feedback comes back there, v1, v2, v3. So this isn't the one that's in the actual book. The one that's in the textbook is the gene regulatory network, but that doesn't matter. Let's do this one, okay? So again, all I'm really interested in is this. Okay, all I'm really interested in this, and in particular, I'm interested in the determinant because the determinant gives me the characteristic equation, right? I don't care about the inputs. So let's do this then. So little n is 2 because we've got two state variables. R is 3 and Q, I really don't care. I'll just set it to 1 because that doesn't appear in this relation here. So what is n? N is 1 minus 1, 0, 0, 1 minus 1. Okay. So that's x1, x2, v1, v2, v3. Okay. dv dx equals, so r is 3, and then there's two of them, so this has to be a 3 by 2. So we've got dv1 dx1. I think what I'll do is, excuse me, what I'll do is I'll set these to 0 where they apply. Okay, so v1, I'm going to assume irreversibility on these things. Okay, so irreversibility. So this thing here is actually 0. Right, it's actually 0 because of that. The next one will be dv1. Let's just do a different color. The next one will be dv1 dx2. What about that? Let's see. Does x2 affect No, it doesn't. V1 x2 does not affect v1, so that's also 0. Okay, so that's 0 as well. The next one is dv2 dx1. Excuse me. So the x's go down. Okay, so the rows are v1, v2, v3. Okay, and the columns are x1, x2. So what about x1 on v2? X1 on v2, yeah, definitely. That stays there. What about, so this one will be dv2 dx2, x2 on dv on v2. Well, I just said that's irreversible, so that's good. That's going to disappear. All right, let's disappear. Let's put that in green for that. Okay. The next one is dv3. dv3, sorry, x1. Let's put them both in. Get them over with. dx2. So what have we got here? 1 on 3. Well, 1 does not definitely doesn't touch 3, so that's got to be 0. Okay, and 2 on 3. Yes, 2 on 3 definitely is there, so that stays there. So we got that. Okay, so now I need to construct the n dv dx. First of all, though, what is I? I will be a 2 by 2 identity matrix multiplied by s. So that gives me s0, 0, s. Okay, so that's si minus. Okay, so now we have to do the n dv dx. Okay, so let's do the first one. So 1 times 0 plus minus 1 times that plus 0 times that. So that's minus dv2 dx1. Okay, and let's do the next one. So 1 times that plus what times that, that's 0. Okay, 0 times that plus 1 times that. Okay, that's dv2 dx1. And then lastly, that times that plus that times that minus that times that. So that's minus dv3 dx2. Good. Okay. All right. And the whole thing has to be inverted because I'm after the determinant. So if we write this whole thing down first, so we got s. So watch these minuses here. Minus, minus, so that's plus dv2 dx1. 0 minus 0 is 0. 0 minus that is minus vt2 dx1. And then lastly, s minus minus, so it's s plus dv3 dx2. Okay, that's good. In fact, I don't really have to go any further, actually, because, well, I'll do one more step. I know that the characteristic equation is the product of the main diagonal minus the product of the off diagonal. Well, the off diagonal has a 0 there, so the off diagonal is 0. So we just end up with s plus dv2 dx1 times s plus dv3, oops, let's do it again, 3 dx2 equals 0. This has already been factored for me, this characteristic equation. In fact, it's very straightforward. The roots for this will be minus dv2 dx1 and minus dv3 dx2. Okay. So what can we say? What are the signs of these? So x1 on v2. x1 on v2 was x1 on v2 was this one. That was positive. So this is definitely negative. And then x2 on v3, x2 on v3, that's this one here, that's definitely positive. Therefore, that's negative as well, right? There's a minus there, right? Don't forget that. Both of them are negative. Therefore, it's stable. Okay, stable. So it's stable no matter what. Now it is, yeah, it's stable no matter what. The other thing we showed in the textbook, actually, when we did the second order chapter, was that this also hasn't got any damped oscillations either. It's completely monotonic behavior. Nothing very special about it. Okay, so that's that. Now we come to the 3 state variables, and this gets a bit more complicated. This time we're going all the way back to there. We have V1, V2, V3, V4. Okay. Okay, so working out the stability for 3 state variables is a bit more complicated. The problem is we get a cubic. Okay, we get a cubic, so it's S3 plus da da da, da equals 0. So we get something like that. It turns out all the coefficients are positive. Hold on, let me do that again. Are positive. And the condition for stability is A0 times A2 must be greater than A0 times A3, where this coefficient is A0. And since we'll ensure that that coefficient is 1, it basically reduces to A1, A2 must be greater than A3. Now, that leads to a fairly involved expression, and I'll write it down here. One thing we will do is we set all the elasticities except for the feedback elasticity. We'll set it, that'll be less than 0. All others will equal 1, which is not unreasonable. Basically, are all first order. And every time we see a term such as this, okay, ij, we will swap it for vi over xj epsilon ij. That comes about because if you remember, dxj xj vi equals epsilon ij. If I rearrange that, I will get, well, you rearrange it, of course, you divide both sides by, just divide both sides by xi, multiply both sides by vi, and you'll get that. So every time we come across one of these, we'll insert one of these, okay? Where these elasticities are 1, we'll just eliminate them. These factors we will call F, and there turns out to be, how many of them? Let me just check. 3 of them. F1, F2, and F3. And when you do this to the characteristic equation, you end up with, let me just write this out properly. So x, that's the cube, plus then the s squared, f1 plus f2 plus f3, plus the s, and then I get f1, f2. If I get all combinations, f1, f3 plus f2, f3, plus then the term without the combination, without the s factor, you get 1 minus e1, 3, and that equals 0. So this is A0, which is 1, of course. This is A1, this is A2, and this becomes A3, okay? And so we use this expression then. We take all these coefficients and put into that expression, and you get something like this. And then we get all these combinations. Oops. Greater than, that greater than comes from this piece here. Greater than F11, F2, F3, 1 minus E1, 3, okay? So remember, these F terms are just these ratios because all the other elasticities have gone to 1, right? So each F term, there's only 3 of them, are given here, okay? All right. Now, the next thing we can do is we divide both sides by F1, F2, F3. And when that happens and you multiply out, you get something like this. Oops, that was wrong. This actually simplifies quite a bit. The other one is F3 over F2 plus F2 over F3 plus 3, 2 ones appear. That's greater than 1 minus epsilon 1, 3. Okay. Now, what's interesting about these terms here, each is the inverse of the other. And it's known that if you have the reciprocal of a number plus the number is always greater than or equal to 2. So this basically matches that pattern. And so each of these they can't be less than 2. So this has to be greater than or equal to 2. This has to be greater than or equal to 2. This has to be greater than or equal to 2. So the smallest value on the left-hand side is 6 plus 2 greater than 1 minus epsilon 3. Okay, that's the smallest it can get. If I take 1 over to the other side, let me see, did I get that right? Not quite. That is this piece here, of course, is a 3 from here. Okay, 3. So if I take 1 over to the other side, I basically get 8 greater than minus E1, 3. And this is the condition for stability. Okay, this is the condition for stability. And basically it tells us so long as epsilon 1, 3 is greater than minus 8, the system is stable. Else, it's unstable. Okay. So that's basically the condition for a 3-state variable. The proof is a little bit more involved, but it can be done. So I just wanted to show you that. I have a similar version in the textbook, but it's slightly different where it uses genetic networks, but the approach is exactly the same. Okay. All right. I think we'll finish there and get this uploaded.